Okay, welcome back. So we have now a panel discussion where our panelists, the experts, are Engineer Ahmed Salim, Engineer William Slater, Engineer Sameh Zaghloul, and Engineer or Dr. Alain Chancey. Um, the title of the panel is What Can Quantum Do for Society? This is actually very important because whenever you try to do something for the industry or for an institution or for the society, people are reluctant to invest in the future. There are certain stakeholders who are definitely investing in the future, like IBM, like Google, those giants. But when you try to do something using quantum computing for let's say, a customer, uh, you try to convince them that this is going to have a definite future and people want to do some investment that they want to see the return for shortly, not in the future. So I think this panel discussion is going to be about this topic. And I'm interested to listen to Engineer Ahmed Salim about his view on this and the view of IBM and what you usually get confronted with when you offer a project using quantum computing for a beneficiary or to a customer.
Thank you, Professor Ahmed, for hosting me. Thank you for Dr. Taha and all the organizers, Professor Haytham as well, for having me here in this school. So it's a very important question because any technology, the ultimate goal out of it is what is the benefits, and this will be can be addressed in different levels. In the day-to-day operation for people is something direct can affect their day-to-day. Or it is a beneficial for enterprises, industries, countries. So we have different levels, and I might start with the one that you just mentioned for people. Yeah, before everything, how this will impact the day-to-day life of people. So if we will look into the use cases, what people want better services, lower cost, and longer life. Maybe these are the main three pillars in my point of view. So how we can give them a better services, how we can give them a reasonable service to help them survive, lower cost and supply chain. If I go and buy something, this price of this stuff or the material that he's trying to get, definitely affected by many factors. One of them, the supply chain, and what we are experiencing now in the real life of the problems and obstacles that we have in the supply chain. If we can optimize the supply chain, so definitely this will affect the cost of the goods or the materials that the people are trying to get. So if we have an optimization problem, how we can make the supply chain more efficient, which means a lower cost of shipping the goods, and at the end, this will affect the cost. So this is one of the use cases for quantum. We can use an optimization, the quantum and optimization problem, to be able to address one of these problems. Definitely better services. The research that has been done and the electric vehicle, for example, seeking for a better electric vehicle battery and longer life batteries. Maybe this will give them a better service when they acquire a car. This will definitely give them a cheaper cost. And the longer lives, and this is, I think, one of the most important part, where we can have some advancement when it comes into the drug discoveries and pharmaceutical industries, where we can have some medicines maybe tailored to people, because as we know, it's a common here, if you have a medicine, it has side effects. So what if we can have medicines and drugs, it's tailored based on the genome and the DNA of the people, so they will not have these direct side effects, and maybe this will definitely even affected the cost of the medicine itself. The medicine and the drug industries, it has a lot of years to be able to issue such a successful drug, for example, or vaccine. So in my point of view, and on the people level, definitely they will not see the quantum as we can see the AI, for example, or laptops or whatever that we are dealing with day to day, but they can feel the effect. Definitely different levels on the investment or the industry level. The companies that work on optimization, simulation, and AI, definitely they will get a huge advantage for the computational power. And thank you for your explanation in the first presentation, highlighting how we can advance these industries using quantum and HPC as well. So this is in short what I can see in this part.
Thank you, Engineer Ahmed Salim. Dr. Taha, would you like to lead the discussion on the next question? Attendees, you may also post your questions in the chat. You don't have to wait until the end because this is a panel, so it is actually designed to discuss issues together. I also see that Dr. Slater started answering in the chat about some of the questions that we missed in the previous session. Thank you for that. Dr. Taha, you are muted.
And Dr. Slater is also among us with the panel, so hopefully his video is appearing. I tried to make a spotlight for everyone in the panel, but it was very hard in Teams to do it. So, yeah, so I lost the hope after all. Okay, so for the second question, I can direct it to for Dr. Slater. Indeed, what will be what's your expectation about the future of quantum technologies, and which one you are gonna bet it will be the winner? Yeah, so you come from the cloud computing at Microsoft and from different backgrounds, and now you have the Chicago Innovation Park next to you with PsiQuantum in it. So do you bet that PsiQuantum will be the one that will lead, or which technology and which yeah, and we don't want to say which company, but which track of architecture?
Sure. Can you guys hear me okay?
Yeah.
Good, good. Yeah, I've got a few things to say about that. First of all, I want to applaud the people putting this on, and also everybody attending. I love my country and I love my countrymen, but I don't know an event in America where we could get so many people to donate their Fridays and Saturdays to this type of effort. My countrymen are too involved in Netflix and video games, and I think a lot of opportunities are going to pass Americans by if they don't get it together quickly. The other thing, I think we're in kind of a narrow window right now, because I don't see a lot of AI programs right now writing quantum algorithms and quantum programs. So I think that if you guys embrace this opportunity and you want to become the experts on exploiting the strength of quantum computers, there's never been a better time of that in computing history than right now, because you guys can become the leaders worldwide. I do want to make a couple of comments real quick. We have the old U.S. Steel plant. I think that plant is extraordinarily large. I think it's well over 300 acres. And here's what's staggering. It is a combination of federal, state, and local money that's going to build this thing up. But it's very, very political. The governor of Illinois is involved, the mayor of Chicago is involved, and even the Trump administration is involved. It is a $9 billion project. So it's arguably the largest quantum project in the United States and perhaps the world. I will give you guys a picture of Chicago because I've been here almost 40 years. Um, if your mom and dad spend $250 to $500,000 to help you get your PhD, there's a lot of people that are not going to want to go to that area of Chicago where this campus is going to be. They will telework or whatever. It's dangerous down there. We have a lot of gang activity. We have a lot of shootings and killings. That part of Chicago is a dangerous place. But if you can get a stake in the quantum industry in America, whether it's outside the United States, I know that most of you are from the Middle East or Egyptian citizens. If there's some way you can get your foothold into the American quantum market, that is a very good thing. We just woke up about 2 to 3 years ago, and the Trump administration, this is all under the U.S. Department of Energy. So the Undersecretary of the U.S. Department of Energy is the guy funding the quantum development. And here's what their thinking is. If you are a quantum startup in America, they don't want you starving and eating ramen noodles. They are going to fund you with about $110,000 or $120,000 salary and give your small company $150,000 operating budget. So the United States is setting the precedent worldwide to put money into the development of quantum. And why are they doing that? They're doing that because they know that that's where the future of computing is. And I put a post in the chat where I said, quantum is the future of computing, and the people in this course are the future of quantum. I really meant that. And as the gray whiskers might give away, I've been in computing and cybersecurity since I entered the Air Force in July of 1977. So I've seen everything. I've worked in every paradigm, and I have this mindset where I'm going to overcome it and be victorious through every paradigm, and that especially includes quantum. I'm totally intrigued by it. I love it. I go to probably 4 to 6 quantum meetings every week. I'm presenting downtown next Wednesday. But this is not about William Slater. This is about embracing the future with excellence and saying nothing is going to stop me from being successful in this next paradigm. So I just want to say it's extremely inspiring to see all of you guys here, and I hope you keep plugging away. You have excellent leaders like Alan Chansey and Taha, Dr. Taha. These are amazing people, and I don't just know these people as names. I've had dinner and hung out with Dr. Taha and his family in Amsterdam. So these guys are rock stars. Embrace everything that they say and jump on these opportunities, because this is a golden opportunity, and an opportunity like this may never come along again. So you were meant to be here for a reason, and just keep plugging ahead and being excellent.
Thank you very much, Dr. Slater. We want to have another angle of the discussion, and I would direct this angle to Engineer Sameh Zaghloul. Quantum computing has active work in the development of hardware and the development of software. Now the question is, for a building up a nation like Egypt, should we invest more in the development of quantum computers, or in the development of quantum computing algorithms, or both? It looks like if you put everything in the quantum computers and you don't have the solutions, then your quantum computers will be sitting still. But if you put everything in the quantum computing algorithms, and you don't have your own quantum computers, maybe nobody is going to be willing to run your algorithm on their computers. So how would you, we are on the other hand, of course, having limited resources. We cannot invest as much as the United States or similar rich countries putting so much money into this direction. So how would you strategically define your thoughts about this kind of development?
Very challenging question, Dr. Ahmed, of course. But let me put it this way, actually. I just came through a recent business survey that states that investment to revenue ratio for quantum computing is something like 18:1. This means that there's huge investment by top companies, of course. The revenues are still coming within the next coming years. The reason here actually is this is a must bus to go. There is no actually choice because this is the future. Okay.
I agree.
About actually investing, like actually you cannot invest universal quantum computing because this will need huge investment. The first thing actually is that we should know, we should do is exactly like this Cairo University Summer School is talent development. We need actually to have a good base, starting base for talent to do development in all directions. First direction of algorithm development, of course, because this is one of the booming areas, because we don't have algorithm ready for all the business problems that we need to solve. So this is ongoing and dynamic area, but the world actually is going this direction. By algorithm development actually is this is IP, and we can actually use this as a product actually, IP for algorithm development to be used in Egypt and worldwide. The second part is dedicated hardware chips, not universal quantum computer, but dedicated hardware chips like ASIC chips, ASIC dedicated circuit burned on a board that do a specific function. As the two famous examples that already very, very popular, and there is a lot of startups worldwide doing this in area of computer security. One of them very popular, quantum random number generator using photonic chip to generate physical unpredictable random sequence. This is very important, and everyone in the world needs this. A second one is quantum communication, and here we are talking about using a quantum technology in providing much more higher secure communication, which is quantum key distribution hardware. So this is just two examples of specific dedicated hardware chips that you can invest. And we do have the facilities if we consider, for example, photonic qubits.
So you are advocating the development of hardware in specific components of quantum computing systems, for now at least.
Sorry, Dr. Ahmed, I didn't hear your last statement.
I was commenting on your answer. I thought you stopped. Maybe it was the network or something. I thought you finished. So I was commenting, highlighting that maybe you intended to advocate the development of specific components of quantum computers rather than the development of an entire or a comprehensive quantum computing system. Is this what you meant? Can you hear me?
Sorry, it seems we have something in audio. Sorry for asking you again to repeat, Dr. Ahmed.
Okay. I thought, first of all, I thought you finished your answer or you finished your talk. So I was commenting that trying to conclude what you meant. Maybe you meant.
Thank you very much.
Maybe you meant that instead of investing in developing a comprehensive quantum computing system, you meant to concentrate or advocating for the development of specific components of quantum computing systems. Is this
Exactly
what you meant?
Yes, exactly, Dr. Ahmed. Like, for example, quantum random number generator, quantum key distribution, and also quantum sensing devices.
Okay.
Which
and
is
then
feasible,
this becomes
actually.
like a stage where you later can aggregate the components to try to develop a comprehensive quantum computing system.
Not necessarily, because each one of these dedicated quantum chips, actually, or quantum systems, has its own use case. So it is a product and has very useful value by itself.
Okay.
But of course, it is one step on the way actually to develop.
Okay, understood. Dr. Taha, would you like to raise the next point?
Yeah, sure. Thanks, Dr. Ahmed. Indeed, having or developing a specific component that will be great from one of the verticals in the industry. So that will support, for example, the cybersecurity or the integration between the hardware and software. However, my next question will be, since now we are gonna go into enabling the specific component would require the development of an ecosystem around it to enable the labs that develop this specific component and would require quantum computing knowledge in general from hardware and software. And then I can direct the next question to Ala. What will be your perspective on what we need in order to have to develop, for example, hardware for cybersecurity from workforce point of view and the technicality that are around it? And do we need really to push forward for one specific direction, like to develop a certain type of hardware, or we need to let it go and go in different directions, and that would benefit this specific vertical in the industry?
Oh, thank you very much for having me. I think, Taha, you actually gave a good answer in your question. I think diversity and competition are key success factors. I think what I can say from my perspective, with my experience in management consulting, is something really important, and we have got a return of experience from generative AI projects, which unfortunately many of them fail miserably because of poor vision, poor project management. I think now the trend is to integrate quantum computing in an ecosystem comprised of high performance computing, HPC, and AI, and there are and it's very good as compared to 2 years ago, where quantum computing was more or less considered in isolation, or even worse, competing with HPC. No, the idea is to combine all that, and the ecosystem. From a workforce point of view, you need the critical mass of expertise, starting from the end in mind. That is to say, and I will focus on quantum chemistry or quantum molecular dynamics, because it's my area of comfort with you, Taha. There are at the moment a very interesting computations that are slightly beyond what can be achieved today, even with the most powerful high-performance computers. And the advantage with quantum chemistry is that we can start from first principles, hence the name quantum chemistry. So we don't need huge amounts of data to load into a quantum computer to run some interesting calculation. And there are competition. Q4 Bio, for example, is a good example, which we discussed during a recent podcast. And so I think competition with a clear purpose, like a challenge, is a very good starting point. And then all the key components, both human and hardware and software, will come into play, and who knows? It's too early to say which technology will be the first to deliver value. That is to say, to enable solving a problem or gaining some insight beyond the current knowledge, or performing a computation faster than what can be achieved today, or, and it's not necessarily the same optimization point, computing at a lower energy cost. And it is very important, because today we know that there is kind of a wall with generative AI because it requires too much energy and it's not sustainable. So that's my answer to you, Tara. Let competition and the ecosystem of people and expertise and hardware and software providers will come together. And I think this event that you co-organized is a very good illustration of how to get things moving. So thank you, and I hope this satisfies your curiosity.
Thank you very much, Dr. Chancey. Actually, I see that some people are asking questions in the chat, but our experts are taking on the questions also in the chat. Dr. Slater and Dr. Taha answered some questions. I wonder if there are, I'm scrolling to see if there are other questions that our audience, is any of our audience have a question to post in the chat or raise hand or something?
Maybe the question of Dina then, because it's mainly related to the different types of architectures.
Yeah. Okay, so the question was, I was lucky to attend a session about quantum computers. It focused more on the different types of quantum computers rather than, oops, chat disappeared, I don't know why. Okay, it's back. Apparently somebody else was asking another question. Okay, it focused more on the different types of quantum computers rather than the math or deep theory. My question is, does the same quantum science apply across different implementations?
So I kind of started the ball rolling in this, and presumably I would think Ahmed or Ala or William can add, and also Engineer Sameh indeed. So in the presentation, there is different, of course, the abstraction layer is the same. The only thing is the implementation is different from the compilation, how to translate or execute the circuit, the algorithmic circuit on the hardware. So when we come to this, every hardware has its own technology, and the main distinction or obvious distinction is called the native gate set. So you have certain gates you need to execute for your algorithm, and every hardware has its own native gate set. And if you don't have this native gate set or your algorithm is not optimized for this, the compiler will need to do a lot of work. This is why it's called the transpiler. There is some translation and some compilation to be done to translate your algorithm into the gates that the hardware can understand. So if your hardware doesn't support certain gate and you are using this gate quite extensively, this means that the transpiler will need to approximate your gate with the native gate set for this particular hardware, and that might be overhead for the hardware. So yeah, and feel free from the audience if you like to add.
So I can take the lead in this, if you allow me. So this is a very nice question, and everyone step into the quantum world is asking this, and this is very critical because we have many players in the quantum realm, and these players, everyone is has an advantage and has his own for example, reasons why he's taking this approach. For example, if we will take IBM as an example, we are building our quantum computer based on the superconducting. Okay, why IBM is taking this approach? because as you know, IBM, it's like started off with a hardware company, so they have many patents on the hardware and they have accumulated experience on this. And depending on this experience, they saw that the superconducting is the winning horse. Okay, it's a competition open for everyone. Everyone is trying to excel, but this is what IBM is thinking of. And each technology has a pros and cons. Yeah, and for example, the superconducting, one of its cons, obvious cons, it's high noise. It's noisy systems, and but the pros, it's scalable, as we can see in the roadmap. And we have definitely different technologies that's like trapped ion, where it has its pros and cons as well. So some companies, they are working with the trapped ion, like IonQ, for example. The pros is it's a stable environment that they can run quantum algorithms, but the cons, maybe it's in a scalability a little bit hard. So, and each vendor is trying to working on his approach and to take through and overcome these limitations in their systems. So it's a completely a new field that everybody is trying to have an approach. And as I mentioned, they have their own reasons. And we cannot judge that one of these architecture are the successful one. By the way, might be all will be successful and based on the use cases. Maybe IBM can succeed on an optimization algorithms, so the superconducting is the best architecture to solve these problems. Maybe the ion trap, it will it will break through in the maybe, for example, in the simulation, so and so on and so forth. I want to relate this as well to when we reach the quantum advantage. Like, it's the same story. It will not be overnight. It's per use case, maybe per field. We don't know yet a tangible answer or absolute answer. As I mentioned, it's a race. It's an open for everyone. At the end, the humanity is the winning. It's not only the vendor, but we as a human, we are the winner, because all these are working to give us a better life. So this is, in my point of view, answering the question.
Thank you, Engineer Ahmed. I see actually several ones in the audience are asking in the chat about a roadmap for undergraduate students to get into the area of quantum computing. Should they be coming from the computer science or from physics or from where? So what do you think, Dr. Slater? Do you have an input on that?
Sir, could you repeat the question?
Several people in the chat are asking about a roadmap for an undergraduate student to get into the area
Sure.
of quantum computing. Would it be better coming from a computer science background or from physics background or double major or what?
Well, I'm kind of old-fashioned. And by the way, I do not have a PhD, but I have 3 master's degrees. And I'm gonna make a statement here, and I want you to listen, everybody to listen carefully to it. I mentioned that I attend 4 to 6 quantum meetups every week. This field is changing extremely fast, and just a personal ego thing. I enjoy trying to be the smartest guy in the room, but in order to try to satisfy my ego and be the smartest guy in the room, I'm playing catch up all the time, even though I got 3 master's degrees and 88 certifications. Personally, a very honest statement, I feel like I've never got out of high school. That's how fast all this stuff is changing. And you're not going to be able to go get a master's in computer science or spend all this time understanding quantum physics and feel like you have arrived. You're going to have to get very, very intense about this. I invite everybody to go to billslater.com/quantum. I just updated my page yesterday, I think, with all these sources, and I'm very open. I share, what I learned, but you're not going to feel like you have arrived. And we got Dr. Taha on the call, and also Elaine Chauncey. I know that we share stuff back and forth all the time. We're friends and colleagues. I'm sure that if you cut off Dr. Taha from the internet and he could not continue to add to the immense knowledge that he has, he'd feel the same way as I do. He would just freak out because he would say, "Hey, you're stopping my growth." So growth is an imperative. The other very important statement I'll make is that the foundations of this stuff go back to the Solvay conference in 1927, when you had all the giants. About 35 of the people that were at this conference got Nobel Prizes in physics and or chemistry. Madame Curie, who was friends with Albert Einstein, she was the first human being to get a Nobel Prize for her work in radium. She got a Nobel Prize in chemistry and also in physics. She also died from exposure to radioactivity, which is a very unfortunate thing. But those were the people that laid down the foundation in the early 20th century for this stuff. And the reason I bring this up is this: even though we've got all these different competing models for qubits, ion qubits, super cold qubits, room temperature computing, it's important for you to understand the fundamentals. And there were some books written. You can go look it up on my website at billslater.com/quantum. There were some books written by a guy named Collingsworth back in 1999 and 2000. And the reason I'm bringing this up is this: if you're going to sit down and discuss quantum with somebody, you've got to have foundational knowledge. Because in places like America, we have a 30 or $31 trillion GDP economy. Opportunities go fast, people spend money, but you don't want to be known as a faker or a person who's just doing bluffing your way through this field. You've got to understand the fundamentals. So, it's a big challenge. It's not the same as classical computing, but you're going to have to work to get there. And I encourage people to go look at my mentoring website and find a mentor that you can trust, and you can develop a trust relationship if you want to accelerate your growth. And the other thing is get some peers. I put links to 6 quantum groups out there. You need to be involved with people, and thank God for the internet, because we could just show up on time, click on a link, boom, you're there in the Philippines, or you're there in Australia, or you're there in Germany, or you're there in the United States. It really doesn't matter. We're at a magic point in the quantum thing where it's a new dawn, and you can learn together with these people. And it doesn't matter if you're in Egypt or anywhere else in the world, you can be part of a group of highly motivated people. So I would say, stay hungry, learn the fundamentals, get a mentor, and just work your tail off. Like I said, as much as I know, I'm feeling like I never got out of high school. That's how intense all this is.
Well, thank you very much, Engineer Slater. If I may add, actually, the same issue exists in computer science and computational science. So, for example, if you want to be a computational physicist, should you be like a physicist and study computer science to be a computational physicist, or should you be a computer scientist and then study physics to be a computational physicist? It works both ways. So define your target, and whether you are coming from one side or the other, you still have another road to go. So it's the same thing in quantum computers. Also, this is my own belief that if you want to go for quantum computer to become just a programmer or an algorithm designer or something is something, and if you want to be a quantum computer scientist or engineer, that is something else. It requires many things to study. I always tell my students at the Faculty of Computing and Artificial Intelligence, especially in the course of computer architecture, that if you intend to be a programmer and you will end up being a programmer of the same quality of a programmer who studied just programming for 2 or 3 months, then there is a problem. You don't need several years studying in computer science to become a programmer as just a plain programmer. But if you are going to be a designer, a computer engineer, a computer scientist, this is something else. So I think the definition of the road is similar also here in quantum computing. Dr. Taha, would you have an additional comment on that?
Yeah, thanks, Dr. Ahmed, and thanks, Bill, for William, for the comment. Indeed, as Dr. Ahmed said, there is 2 different ways, and it happens in computational physics and in computer science. The only thing is that for quantum, because now it's an early stage, you might need to push hard for learning about the other field. So if you are a hardware engineer, so we developed a master in the Netherlands, and there is the students in the first year, they study from both specializations. So that's very important. So for the people who are gonna, or the students who are gonna be specialized in software engineering, they study and do a lot of experiments by hand to learn more about quantum information, how they do the protocol, the transpiling, the operations, and they get a bit of idea about the chip design. So still basic knowledge, but it's very helpful when they are working R&D or multidisciplinary team, where there's a lot of people who might give a lot of points about the hardware and gives them some papers to read or translate into code. So the software will touch at some point about the hardware. So if you go for a software, you need to learn a bit about the hardware and so on. Maybe not, you will decide which limit you are gonna stop at, depending on the level. If you are want to be an algorithm developer, your hardware knowledge will be higher. But if you are a quantum software engineer, you might learn less because you work more about optimization or enabling use cases, and the hardware is sort of like an abstraction layer for you. So it depends on the end goal. But typically, the typical path would require that if you go for a software, you will need to study math, different types of programming, and also the use cases, to learn more about the use cases, like how to apply quantum computing for chemistry, finance, and cybersecurity. And this is where Dr. Ahmed and I, when we worked together with the other brilliant colleagues during the organization of the school, and also we had Engineer Sameh Zaghloul, and also here our colleagues as well. We try to craft the program to reflect on these use cases. So if you, for Egypt, there is not much of hardware, there is a lot of software, and it's nice to learn about how to use the quantum computing in different use cases while you are learning a bit about the hardware. But if you go to the other way, you will need really good, solid knowledge in physics. And then on the top of that, a bit of software. But the one that's suitable now, if you want to start now, you just try to finish the school, learn about that, and then reflect on what you can do from this with this knowledge in the future, and what do you need more. And perhaps it could be future event to complement on that.
Thank you, Dr. Taha. Do we have more questions from the audience? Or
yeah, I think we have one about maybe we have 2 questions will there be ever a general purpose quantum computer? I know that this definition confuses a lot of people in different fields. Yeah, and the second question, how real is the quantum threat to cybersecurity? So maybe we start with the first one, the general purpose quantum computer. And maybe we can direct it to Engineer Ahmed, and then we get an input from Alain, and then for the cybersecurity, we direct it to Engineer Sameh Zaghloul. So yeah, Ahmed, the floor is yours.
Thank you. I'm laughing big time because it's a very tricky question. It has many definitions because it depends how do you see the general purpose quantum computer. So
It
is
doesn't
it a
end this
computer?
question.
Yeah. So there is no like a solid and absolute answer. Still, we are in quantum session. So the uncertainty is the reality here. Okay. So the general purpose quantum computer, if you look into the definition, do I have a machine that I can deploy and solve and run any program like what we are using now, the classical laptops or desktops or whatever? So I have Word, Excel, whatever application, I just download it from the internet, install it and run it, it works fine. I don't care about the underlying hardware, okay? So this is one of the definitions, general purpose. I don't care about the architecture, I don't care about the internal procedures, there are RAM, whatever. Okay, I'm a normal user. I have a program. So still, there is no an absolute answer for this. We cannot judge that there is a general purpose quantum computer. As we just mentioned, we have different architectures, different way of dealing with these architectures. So we are not there yet. I don't know personally if we will reach such a thing, as I mentioned, because there might be a lot of players, winners in the quantum race. So might end up with different architecture running different use cases. So we might not reach this point. I don't know. Again, a general purpose, what do you mean? If I have, for example, I superconducting and IBM, for example, because I know about IBM, we have many use cases across different industries. We have use cases in finance, in logistics, drug industry, supply chain. So these are different industries. We are developing algorithms to solve the critical problems on these domains. So if you are talking about that I can develop algorithms in different domains that can run on a single quantum computer, if you can say this is the general purpose, so the answer is yes. So we can develop different algorithm across different industries, can deploy it on a superconducting machine. It depends how you see the general purpose or define it. This is my answer. I don't know if anyone from the esteemed committee panelists have another opinion. I don't want to steal much time on this.
Yeah, maybe we can get a perspective of Alain and before we go to the cybersecurity question.
So the answer is yes, eventually, and the big unknown is precisely when, according to the plan put forward by IBM, we should enjoy using general purpose, commercially available quantum computer as early as 2029. And I think, honestly, the future is open. I don't think it's predetermined, and I think there are so many other important factors like the integration of quantum sensing and quantum computing. In some areas, it is really a game changer. And if you add on top of that artificial intelligence, it's more than just general purpose. It means it is completely there are completely new applications that we cannot even imagine today, which tomorrow will in a couple of years will become obvious. I mean, think about when I was born in 1958. I mean, and back in the 1980s, it was the era of the mainframe and supercomputers. I used to work for Cairo Research, right? But the invention of the internet and everything that goes along with it was just no one could have imagined the transformation of society, as William said. It changes the way we we work, we behave, all that stuff, and so I think quantum it's beyond the question. It's more than just general purpose. It will change the way we live. It will change the way we work, we collaborate, And I think this is exciting because it's yet to be written, and everyone in the audience should think that they have an opportunity to be part of this transformation. That's my answer. Thank you.
Thank you. Now, regarding the other part about cybersecurity, Engineer Sameh.
Okay, a very interesting point.
How real is the quantum threat to cybersecurity?
Okay, let's start by history. Actually, what is the famous quantum algorithm ever known? Actually, the famous quantum algorithm everyone knows. Actually, Shor's algorithm. Of course, this is more than 40 years now. Okay, this was a turning point because actually this algorithm actually will enable, actually without the algorithm, quantum computer will not be able to break RSA and ES and current cryptography. Okay? So the algorithm is the first part. Okay? And Shor algorithm, actually, this is from my point of view, is a most famous actually quantum computing algorithm ever known. And it was in the 80s, actually more than 40 years ago. This is the threat type. Okay? But on the other hand, quantum computing, okay, will provide more security through using quantum key distribution, for example, or quantum communication in specific, because using quantum communication will prevent any tampering on or leakage or data, okay? Because as simple as anyone try actually to eavesdrop on the connection line, either fiber or wireless, will interrupt the quantum state, will make it collapse, so sender receiver will know. So actually, there is both sides. The threat, because the powerful of quantum computer in solving very, very complex problem like RSA and ES and all known cryptography, okay, cryptography as we know. But on the other hand, will provide much more level of security as well using quantum communication. And by the way, also the second famous quantum algorithm with QKD, quantum key distribution, by Bennett and Brasad, which just actually awarded Turing Award just a couple of months ago. And also this algorithm, this is the way actually to protect your data using quantum computing was almost 40 years ago as well. So actually 40 years ago, we have the two sides of the equation, of the two edges of the sword actually. The powerful, the power of quantum computing to solve problems that classical computer will never solve it in many years, of course, and this is a threat. But on the other hand, there is also, with the right algorithm, of course, because that's why algorithm is the main thing here. Quantum computing actually, or quantum physics, can secure our world. So the threat is here actually, and the window's closing, because till 2 months ago, everyone was expecting what they call Q day, which is the day that we will have a cryptographical relevant quantum computer with powerful enough. We are talking about million qubits to be able to break RSA in near real time. Just less than 2 months ago, this number 1 million, as you mentioned, Dr. Ahmed, actually reduced by 10. It is 100,000 qubit. Okay, and the window actually stayed at 2035 for Q day. We are now talking about 2029. So, for example, a couple of big tech companies actually announced that they will finish migration to post-quantum cryptography by 2029, including Google itself, Ripple blockchain network, and Bitcoin. So the window is closing, and we need to act fast with the migration.
So it is real, but it still opens another opportunity for securing the system from the quantum communication system.
Yes, but also, okay, I know I don't need anyone to panic actually, but there is one before 2029, which is the latest dates that we know so far for Q day. Maybe change actually next month or couple of months, okay? but there is a threat called harvest now, decrypt later, and this has been going actually for the last couple of years. Harvest now means store encrypted data and encryption keys now, and you will solve it a few days after a couple of years. So this is threat, we cannot avoid it. That's why we need to move faster. Yesterday, last year, 2 years ago, actually, in migrating and protecting our critical infrastructure. So this is a critical matter.
Thank you, Engineer Sameh. I think we covered a broad spectrum of concerns and questions here. Do we have something else to discuss, or should we conclude the day and resume tomorrow?
Yeah, not much of questions now in the chat, and most of these questions will be answered anyway during the upcoming sessions. So yeah, so it's now your call, Dr. Ahmed.
Okay, I think we concluded for the day. Thank you very much, everyone, for this very informative, very rich discussion. Tomorrow we will start in the same time, 6 p.m. Cairo time. And then we're thinking the last 3 sessions are going to be Thursday, Friday, and Saturday of next week. They are intentional going around the weekend, so to avoid conflict with the work and studies for people and students. Someone asked here in the chat that they are on the other side of the world in the east, I think in India, where the time is after midnight, which is not very convenient for them. I think next time we need to think about this. But he was asking about the recordings. We will make the recordings available, and we will let you know when the recording will be available and the mode of availability. For today, thank you very much for having you here, the lecturers, as well as the audience. And we look forward to starting the hands-on session tomorrow. Thank you very much.
Thank you.